All right, so this is part 2 of the video. I forgot to actually add the geometry sheet, the one you see right in front of you. So while we're doing the fluid structures, it would help you to have this and your periodic table. Okay, so I'm going to kind of go through these geometry sheets real quick. One thing is we are not worrying about bond angle, any of that hybridization stuff currently. So I'm just going to kind of talk about the general shapes. Okay, so first of all, when you look over the left, you see these numbers here, 2, 3, 4. Okay, it says total electron pairs or domains. That basically means how many things are attached to the center. Okay, so that basically means I have 2 things attached to the center, then 3 things attached to the center. Then your next is the electron domain geometry. I like to think of this as kind of like your base shape. Okay, so like if I have 2 things attached, I'm going to create a linear shape, like a line. Okay, if I have 3 things attached, this is going to be trigonal planar. So tri meaning 3. Okay, so trigonal planar, planar all being on the same plane. If I have 4 things attached, it'll be tetrahedral. Okay, so tetra means 4. 5 things attached would be trigonal bipyramidal. The way I remember that is if you look at this, you basically have a base of 3. And if I were to attach the tops and the bottoms, okay, you basically have you'd have 2 pyramids. Okay, so that's where that kind of comes from. So trigonal bipyramidal. Then your last one is octahedral. So I know it has 6 attachments, and the reason why it is octahedral is because if you were to attach the tops, okay, and the bottoms, you basically have you've got a 4-side pyramid on top, and you'd have a 4-side pyramid on bottom. So 4 plus 4 gives you 8, so that's why it's octahedral. So that is like your base shape. So your electron domain geometry is like your base shape. And then when you come over here to like your molecular geometry, it's more of your specific shape. Okay, so that's based off if all of them are atoms, if there's any leftover pairs. So if I were to look at like trigonal planar, if all these were atoms, so like say this is carbon, and then this is, we'll just say chlorine, and that's chlorine, and there's no leftover pairs at all. That's what we mean by trigonal planar. So if you were to start off here at trigonal planar, you come over here, and you're going to say, is there any leftover atoms, or are there any non-bonded pairs on the central atom? No. Then it's just going to be the same shape. But if you get to where, like, say I have 2 attachments, so say I've got carbon in the middle, and this is my pair of dots that's left over, and then this is like an oxygen, and then this is an oxygen. Okay, that's what that basically looks like, is this little balloon shape you see right here is that leftover pair that's left on the center. Okay, so basically it means I have 2 atoms, I have 2 oxygens, and a leftover pair, which changes the shape. Now all of a sudden I have a bent shape. Okay, so we'll go through these more as we start doing more examples. So as far as the other 2 boxes go, number of non-bonding pairs just means if there's anything left over. Okay, so like linear, there's nothing left over here, so that'd be 0. Trigonal planar would be 0. Now this right here, this is basically what we're talking about. That's a leftover pair, so that means it's 1. This would be 0, this would be 1, this would be 2, it'd be 0, 1, 2, 3, 0, 1, 2. Okay, and this last box is polarity. Now, for the most part, I utilize the pictures as much as I can on here because when you draw it on paper, you got to think on paper it's just 2-dimensional. When you use this, you can actually kind of see 3-dimensional shapes. And for the most part, polar and non-polar will stick true to this shape sheet. Now, there are a couple of exceptions and stuff we'll kind of go through. But if everything looks nice and balanced out like this one does, linear, this would be non-polar. There is no unbalance. Like trigonal planar would be non-polar. It's nice and balanced out. There are no leftovers. But on this one, on bent, I basically have this leftover pair that's creating this negative cloud over here that's going to kind of throw it out of whack. So it means it's polar. Okay, tetrahedral, there's no leftover pairs. It would be non-polar. This would be non-polar. This would be, oh, I'm sorry. Oops, went too fast. Okay, that would actually be polar, okay, because this is throwing it off. Okay, and this is going to be polar as well because you've got basically this giant negative side over here and then the positive side over here. Okay, go on this side, this would be non-polar. This would be polar. This would be polar. Now, this is probably the most confusing one, the linear on trigonal bipyramidal, is this would actually be non-polar. Okay, the reason why is basically you have a positive here and a positive here like pulling their own directions. Okay, so that kind of cancels out that charge. And then you have a negative pull in this direction. You have a negative pull in this direction. And then you have a negative pull in this direction. Okay, so think of it like a tug of war that's going nowhere. So that would make it neutral. Okay, now if I have this octahedral, this is going to be non-polar. Everything's nice and balanced out. Square pyramidal. Okay, this would be polar because this is throwing it off right here. And this square planar, this one's actually going to be non-polar as well because you got to think these positives are going there. Their atoms are going their own way, and they're all canceling each other out. Okay, so this is going up, this is going down. And then usually on these, if like on linear and square planar, if I were to kind of dice that in half or cut it in half anyway, it would be considered symmetrical. So we're going to refer to this sheet quite a bit as we draw these Lewis structures. So we're going to come back up here to the top and start doing Lewis structures. Okay, I will try to go through each kind of like possibility the best I can. Okay, so when you're doing Lewis structures, so remember your first step is to figure out the number of valence electrons. So remember, if you need a recap on that, let me go up to my periodic table real quick, show you where valence electrons are. Okay, you are looking for 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Okay, that tells you the number of valence electrons. So that's what I'm going to refer to. Okay, and remember the perfect number of valence electrons is 8. And so each thing is trying to get to 4 pairs. So we're going to start off with TE. So TE, okay, let me see if I can make this smaller since I'm zoomed in. So TE, if I looked up tellurium on your periodic table, so tellurium, if I go back up here, let me zoom back out. And I won't do this for every single one, I'm just kind of showing you. Okay, so tellurium is up here at 6A, so tellurium's right here. Okay, so if you looked all the way at the top, okay, that would be 6 electrons. Okay, so we're going to come back down here. Okay, so that would be 6 electrons. There's only one of them, so 6 times 1 gives me 6. Okay, and then bromine, if you looked at bromine, it's in group 7A, so that's going to be 7 valence electrons, but there's 6 of them. So 7 times 6 gives me 42. Okay, so add up all my electrons, I get 48 total electrons. Now your next step is divide by 2. So I'm going to take 48 electrons, I'm going to divide it by 2, because we want to figure out how many pairs there are, so 24 pairs. So I got to figure out who's going to be in the middle. Okay, well, if I only have 1 tellurium, it's got to be in the middle. If I have 6 bromines, there's no way I can actually pick which bromine would actually go in the middle. Okay, because if you've got 6 of them, how would you decide which one goes in the middle and the other ones get left out? So if I've got tellurium in the middle, I'm going to attach 6 bromines. That's your first thing you're going to do. Okay, now each one of these lines right here counts as a pair of electrons. So basically what that's doing is I'll kind of use a different color. Oops, just deleted all that. Okay, basically what's happening is this line is showing that basically 1 electron's coming from tellurium right here and 1's coming from bromine. 1's coming here, 1's coming here, 1's coming here. So it's basically just a shared pair. Now, a good way to check yourself is, remember, tellurium has 6 valence electrons. So right here, remember, we have 6. So if I were to count these dots on tellurium, I see 1, 2, 3, 4, 5, 6. Okay, so that should match up. Okay, so let me get my eraser even smaller now. So I'm going to get rid of this. So I basically want to show you how that line just means a shared pair of electrons. Okay, now I've used up 6, so that means I've got 18 left. Okay, now each one of these terminal atoms can hold 3 more pairs. Because remember, the perfect amount is 4 pairs, and they already have a shared pair on them. So now that one gets 3. This bromine gets 3. This does not have to be perfect, but whenever you do on the quiz and test, whatever you're using it for, okay, please make sure you kind of write fairly legible. I know mine's not the best on here. It's kind of hard writing on this iPad. Okay, but as long as we can see where the dots are, that'll help us kind of establish what's going on. Now, I just used up all 18 pairs. Okay, whatever was left, now I have 0 left. There's nothing left over, so nothing goes back on the center. Tellurium, okay, is in the middle. It's got its at least 4 pairs, okay, which let me touch base on that a little bit because that's usually what gets people, is when you go up to the periodic table, as soon as I get there, anything from column 4A over, so carbon on, if it is going to be in the middle, it has to have at least 4 pairs. If it doesn't, that means you've got to move something around to help out. You can't really steal from somebody. We can just shift things around. Okay, boron right here, I do not care. It's fine with 3 pairs. Beryllium is over here, is fine with 2 pairs. It's starting at carbon. If you have something carbon on in the center, it better have 4 pairs, which we'll run into in just a second, and we'll go over how to kind of fix that. So we drew our Lewis structure, no leftover pairs. Total number of electron domains, just attachments. So this would be 6 attachments. Okay, my electron domain geometry, so I would do is I would go down to my sheet. Okay, I would find the number 6, which is right here. Okay, so my electron domain geometry would be octahedral. Now, I did have no leftover pairs, so there was no leftover pairs. They were all atoms. They're all bromines. So my secondary shape, or my molecular geometry, would also be octahedral. Okay, so let's go back up. So this would be octahedral. My molecular geometry would also be octahedral since there's no leftover pairs. Okay, polarity, is it polar or non-polar? So everything looks nice and balanced out. There's nothing kind of throwing it off. So this is going to be non-polar. Now, as far as IMFs go, so we're going to go strongest to weakest. Okay, so it is non-polar, so I know I at least have LDF. Remember, London dispersion is for non-polar or polar. My next option would be dipole-dipole, but that's only if it's polar. So that means this one's actually done. So the only one it has is LDF. All right, let's move on to the next one. CO2, I'm going to say carbon is in group 4A, so that's 4 electrons. There's only one of them, so 4 times 1 gives me 4. Oxygen, each one is in 6A, so 6A, but there's 2 of them, so 6 times 2 gives me 12. Okay, add that up, you get 16 electrons, and then 16 divided by 2 gives me 8 pairs. Okay, so please be careful with, I understand this is basic math, and it can be easy to make little mistakes, which will affect your number of pairs, which will affect your drawing, so it's kind of like a domino effect. So please just make sure you check your math. Also, please make sure your drawing reflects your formula that we give you. There should only be 1 carbon and 2 oxygens. Okay, so it kind of happens every year how we see kind of atoms pop up out of nowhere or even disappear. Okay, so some people get in the habit and they just start doing this. So they just start attaching O's like this. Okay, well, if I look at my formula, I'm only supposed to have 2. So I don't know why I have 4 right here. So just be careful with that because that's an easy mistake. So I am just going to attach 2 oxygens. Okay, that's the first thing I'm going to do. Okay, carbon was in the middle because I only have 1 of them, so I can't pick between the oxygens. I just used up 2, so that means I got 6 pairs left. Okay, the way I teach my class is treat your central atom like the host. Whenever you're a proper host, you always take care of your guests first. So I am going to actually fill up my terminal atoms first, and then I'll worry about my host later. So I've got 6 more pairs, so I'm going to put 3 pairs on each one of these oxygens. Okay, I've used all 6. There's nothing left over. I can't put anything left on carbon. Okay, if I look at both my oxygens, they're happy. They have their 4 pairs. Remember, the whole goal is to get to 4 pairs or 8 electrons. Okay, they've got 1, 2, 3, 4. 1, 2, 3, 4. Okay, so they're content. Okay, but remember what I said about starting at carbon. If carbon's going to be in the center, it needs to have at least 4 pairs. So right now, it only has 2. Okay, I only have this one and this one. Okay, so I got to figure out how can I help this carbon out? Okay, how can I achieve 4 while also keeping the oxygens happy? I can't just steal them. Okay, I can't just take a dot. I can't just take dots from carbon and put them over here. Okay, and then, because it wouldn't work, because oxygen is just not going to give them up like that. Okay, but what we can do is we can kind of borrow or share those. So what I'm going to do is I'm going to take 1 from each side, and we're just going to bump it over and help it out. So this one I'm going to take, it doesn't matter which one you pick. Okay, I'm going to take one of these, and I'm going to shift it over there to a double bond. Now, when you do this, please don't forget to get rid of those dots because they didn't disappear, they just shifted over. I'm going to do this to the same side as well, so now I'm going to create a double bond over here. Okay, and now if you look, carbon has its 4 pairs and oxygen still have their 4 pairs, so that means this one's actually done. Okay, so this one is done now, so everything's nice and balanced out. Number of domains, all I have is 2 oxygens. Okay, so that's just 2 attachments. Now, please be careful. Double bonds don't count as 2 attachments each. So I don't have 4. Okay, it's still just 2 oxygens. Okay, so the way kind of example I think about is when you hold like a pencil in one hand and then you hold the pencil with both hands, it's still just 1 pencil. Okay, I can't just say now it's 2 pencils because I have both hands on it. So there's 2 attachments. Okay, if you go down to here to the shape for 2, this would be electron domain geometry would be linear. And you look over here, the only other option for my molecular geometry is linear. So let's go back up here. So this would be linear. My molecular geometry will also be linear. Polarity, it looks nice and balanced out. All the oxygens, everybody's good, so there's no imbalance. Okay, so this is going to be nonpolar. If it's nonpolar, the only possibility it can be is LDF. Okay. Let's move on to the next one. So we got NH3, so nitrogen has, I'm going to kind of start moving a little faster now. Nitrogen's got 5. There's only 1 of them, so that's going to be 5. Hydrogen has 1, but there's 3 of them, so 1 times 3 gives me 3. That gives me 8 total electrons. 8 divided by 2 gives me 4 pairs. Okay, I got to figure out who's going to be in the middle. I only got 1 nitrogen, and then hydrogen will never be in the middle. It's too small. Okay, so I'm going to attach my 3 hydrogens because that's what I have. Now, I've used up 3 pairs just then, but I've got 1 pair left. Now, I cannot put any dots around hydrogens. 1, how would you pick which one gets it? Okay, and 2, hydrogens are too small. They're not going to be able to contain that. So if I can't put that one last pair on any of the hydrogens, any leftovers go back on their center. Okay, now I like to circle this just so you can see it. You don't have to. It just helps me see because when I do my attachments, like my next box, I have 1, 2, 3, 4 attachments. So this would be 4 of my total number of electron domains. Okay, now I'm going to go to my shape sheet for 4. So 4 is tetrahedral. Okay, so my electron domain geometry is going to be tetrahedral. But remember, my picture was like this, so I'm going to draw it here since that's basically what it is. I've got 3 H's attached, and I have a leftover pair. Okay, those are not all atoms, so it cannot be tetrahedral again. It's actually going to be this one, trigonal bipyramidal, because remember this little balloon right here is basically that leftover pair. And all these are basically my H's. And then N is in the middle. Okay, so my new shape, or my molecular geometry, is going to be called trigonal pyramidal. Okay, so I'm going to go back up here. Okay, so first of all, 4 attachments would just simply be tetrahedral. Now my molecular geometry is going to be trigonal pyramidal. I'm going to come over here. Is it polar or nonpolar? This is not balanced out because of that electron pair right there. So this is actually going to be polar. Now, I'm going to start off. We know it's going to be LDF because that's polar or nonpolar. Now, since this is polar, I can also go to dipole-dipole. Okay. Then my third option was, is there a hydrogen bonded to an N, O, or F? Okay, well, I have a hydrogen bond to an N, so it has a hydrogen bond as well. So it actually has all 3. So if I were to ask you between this one and this one, which one has a higher boiling point, it would be this one, okay, because it has all 3. Okay. All right. Let's see, ICl3. Okay, so iodine has 7. There's only 1 of them, so that's 7. Chlorine's got 7, but there's 3 of them, so that's 21. That gives me 28 total electrons, so that gives me 14 pairs. Okay, so iodine's going to go in the middle. I'm going to attach 3 chlorines. Okay, so I've used up 3. I have 11 left. So I'm going to start filling up chlorines. I've used up 9. I've got 2 left. Chlorines are full, so the only place I can do is put them back on the center. I'm going to go ahead and circle them just so we don't forget they're there. So now if I were to ask how many things are attached, this would be 5. Okay, so the shape for 5, I'll do this for a couple more times and we'll kind of start moving faster. Okay, so ICl3, so I have 5. My shape for 5, okay, would be trigonal bipyramidal. Now, if you looked, I had ICl3. I'm not going to draw out the whole thing again, but I'll just kind of give you the gist. I had 2 leftover pairs, and I had 3 atoms. So that's basically what's going on over here. You have a chlorine here, chlorine here, chlorine here, and then you had these 2 leftover pairs right here. So my new shape is actually T-shaped. Okay, so we'll go back up here. So this will be trigonal bipyramidal. My new shape is called T-shaped. Now, polar versus non-polar, this is definitely going to be polar because you've got both of these electron pairs kind of throwing it off. It's not balancing out the chlorines. So this is going to be LDF because that's non-polar, polar. It's polar, so now I get a dipole-dipole. But I don't have a hydrogen in there anywhere, so I had to stop there. Okay, CF4, so C's in the middle. Okay, well, I'm kind of jumping ahead. So carbon has 4. Fluorine has 7, but there's 4 of them, so that's 28. It gives me 32 electrons, so that gives me 16 pairs. So I'm going to attach 4 fluorines. I'm going to fill them up. All right, and I've used up all 16, so there's nothing left over, so that's done. So that means there's 4 attachments, there's 4 fluorines. Remember, 4 was tetrahedral. And since there are no leftover pairs, they're all fluorines, it's going to be the exact same shape for my molecular geometry, so tetrahedral again. Everything's nice and balanced out, so this will be non-polar. Okay, and then if it's non-polar, the only thing I can have is LDF. All right, this one's a fun one. So N2, okay, so nitrogen has 5, but there's 2 of them, so that's 10 electrons. Divide by 2, you're right back down to 5, so that kind of step is redundant. So the way I do this is I attach an N to an N first. Okay, now I'm going to pick one to fill up first, and then I'm going to put the leftovers in the other one. It kind of gets a little bit more difficult if you try to give one here, one there, one here, one there. So what I'm going to do is I'm going to fill up this nitrogen first. I just used up 3. So far I've used up 4, so I got 1 left. So I've got 1 left to put there. Now if I look, this nitrogen right here is content. It has 4 pairs. This one is not. It's basically only has 2. So I got to figure out how can I help? Like how can I help that nitrogen out? So it needs 2 more. So I'm going to do is I'm going to bump 2 of these over to help out. And this actually creates a triple bond. So now both nitrogens are balanced out. Both of them have their 4 pairs, so they're nice and content. Now, there's only 2 atoms here. So anytime you have 2 atoms attached to each other, there's only going to be an attachment of 2, which would be linear. There is no other shape for linear besides linear. This would be non-polar because everything's nice and balanced out. And then all it would be is LDF. Okay, next one, H2S. Hydrogen has 1, but there's 2 of them, so that's 2. Sulfur has 6, but there's 1 of them. So that's just 6. Add it up, you get 8. So that 8 divided by 2 gives me 4 pairs. So I figure out who's going to be in the middle. We know hydrogen can never be in the middle, so it's got to be sulfur. So I'm going to attach the H's. I've used up 2, so I got 2 left. Okay, I cannot put any dots around hydrogen because that's all they can do is that line, so that means leftovers go here. Now, I'm going to circle these because that means I have 4 attachments, or 4 electron domains. So this would be tetrahedral again. But if you refer to your shape sheet, I've got 2 leftover pairs right here, and that's actually going to be called bent. So I'm going to kind of speed things up and not go back and forth all the time. So that'd be bent. Now, even though you drew it this way, okay, it looks symmetrical, nice and balanced out. But if you were to look at that shape sheet, For bent, it is not balanced out, so this is actually going to be considered polar. Okay, so you got to kind of watch out for that. So I'm going to see what I have. I know I have LDF because that's for non-polar, polar. This is polar, so it definitely has dipole, dipole. I have hydrogens, but they're not bonded to an N, O, or F, so I have to stop there. That's all that's there. All right, PCl3. Okay, PCl3, so phosphorus has 5. There's only one of them. Chlorine has 7. There's 3 of them, so that's 21. Gives me 26 electrons, and that gives me 13 pairs. So P is going to go in the middle. I used up 3. I got 10 left. I'm going to fill up each one of these chlorines. Used up 9. I got 1 left, so that means leftover is going to go back on here. Okay, so I have 4 attachments. 4 attachments would still be tetrahedral. Okay, now since I have leftover pair, my new shape is called trigonal pyramidal. And again, this kind of helps if you have your shape sheet available if you're working on this while I'm doing it. It is not balanced out. This is polar because of that leftover pair. So it's going to have LDF, dipole, dipole. And then do I have a hydrogen bond to an N, O, or F? No, I do not. So that means it's done. Okay, so we'll kind of skip around a little bit. Well, go ahead and do this one. XeCl4. Xe has 8, so xenon has 8. There's only one of them. Chlorine has 7, so it ends up being 28. Comes out to be 36 electrons, which comes out to be 18 pairs. Xenon's going to go in the middle. I just used up 4, so I got 14 left. I just used up 12, so I got 2 left, so that means I got to put leftovers back on the center. Okay, I'm going to circle them so I don't forget they're there. So that means I have 6 attachments now. 6 attachments would be octahedral. Now remember, this is kind of one of our special ones where as far as polar and non-polar goes, because remember we have 2 leftover pairs, so we're dealing with this square planar. So since everything's kind of pulling its own direction and kind of neutralizing itself, this one's going to be non-polar. Oh, sorry. Square planar is my next one. So square planar. This would be non-polar. So the only one present would be LDF. All right, now let's skip over to, let's do HF. So hydrogen has 1. Fluorine has 7. There's only one of them. 7 plus 1 gives me 8. So that means I have 4 pairs to use. So I'm just going to attach an H to an F. Now, I've used up 1. I've got 3 left. Now, I cannot put any on H. So that means all 3 pairs get to go to this fluorine. And that means I'm done. There's no leftover pairs, so it's 0. Now, number of attachments, anytime I have only 2 atoms, it's only going to be 2. Okay, which is going to create a linear shape. Now, as far as polar and non-polar go, does this look balanced out? No. You've got a fluorine that has leftover pairs on it, and you've got a hydrogen off by itself. So if it is not balanced out, I know normally linear would be non-polar, but you can see this is definitely not symmetrical. This is not balanced out. So this is actually going to be polar. So it's going to have LDF because it's non-polar, polar. It's going to have dipole, dipole because it's polar. And I did have a hydrogen bond to an N, O, or F, so I actually do have a hydrogen bond. HCN, H has 1, carbon has 4, nitrogen has 5, gets 10. Divide by 2 gives you 5 pairs. Okay, now I got to figure out who's going to be in the middle. So hydrogen can't be. So carbon or nitrogen. So remember, you want the one that's least electronegative, or you want the one furthest to the left on the periodic table. So that's going to be carbon. So I'm going to put nitrogen on the outside and put hydrogen on the outside. I've used up 2, so I've got 3 left. Now, hydrogen can't take any, so I'm going to go ahead and, remember, you got to take care of your guests, so we'll worry about carbon here in a minute. Okay, so nitrogen used all 3, so I got none left. Now, if you look, hydrogen's good, nitrogen's good, but carbon only has 2. So that means we got to bump 2 of these over here to help out. And that becomes a triple bond. When you do mow those, please do not forget to erase those dots, because if you leave those, now you have more pairs than what you started with. Now, I've got 2 things attached. Okay, I have a hydrogen and a nitrogen. That triple bond does not count as 3. It only counts as 1. So this would still be linear. Okay, this would be considered polar because that is not balanced out at all. So this would be LDF, dipole, dipole. Now, I do have a hydrogen and a nitrogen, but they're not bonded to each other, so that does not count. So that means you got to stop there. Okay, so move on next. See if I can find a good one. All right, so as far as these go, right here, these polyatomics right here, there are different ways to do this. I'm going to kind of show you my way to do it. If there's a way that you do it, that's totally fine. Okay, I don't want to mess with your way if it works. So what I'm going to do is I'm going to count my electrons just like normal. So phosphorus is going to have 5. Okay, oxygen is going to have 6, but there's 4 of them, so that's 24. If you were to try to add those up, you get 29. 29 divided by 2 is not good because you get a decimal. But this minus 3 right here means I have 3 extra electrons. So I'm going to add 3 in the end, so I get 32, which is a nice number to divide by 2 because now that gives me 16 pairs. So phosphorus goes in the middle. I'm going to attach 4 O's. Okay, I've used up 4. I got 12 left. I'm going to take care of my oxygens. Okay, I've used up 12, so I have 0 left. Now, this is in my class, I usually call this like the oxygen trick, is that normally when we deal with oxygens will double bond, usually whenever you're working with them, unless there's electrons in the way. And this right here basically tells me how many extra electrons are going to be in the way. So if oxygens normally double bond, this 3 right here is going to tell me how many will stay a single bond, and the rest will become a double bond. So I'm going to pick 3 of these to leave alone. I drew them fine, just leave them alone. Okay, that means one of these I've got to switch to a double bond. Doesn't matter which one, I'm just going to pick the top one. Okay, so what I'm going to do is I'm just going to shift this around and turn that into a double bond. Okay, so that means this one is done. So you just put this in a bracket and you put a -3, and that's it. Now, if you wanted to check yourself, remember phosphorus has 5, right? Okay, so if you were to count 1, 2, 3, 4, 5. Oxygens normally have 6, so that's why you have 1 right here, 2, 3, 4, 5, 6. Okay, that's if it's a normal oxygen. In this case, I have 3 extra electrons. So that means 3 of these oxygens have to be off somewhere. There has to be electrons somewhere. So if you counted each one of these, you would count 1, 2, 3, 4, 5, 6, 7. So it's normally 6, but not 7. So that's where basically what's showing is where those electrons are. Now, as far as attachments, it's still just 4 oxygens. So that's going to be tetrahedral. And then it's going to be tetrahedral again. Okay, now even though those are 4 oxygens, they are not all the same. Okay, 3 of them have an extra electron and 1 doesn't. So that means this is going to be polar. Okay, so it's going to have LDF. It's going to have dipole, dipole because it's polar. And there's not a hydrogen in there, so I can't go to hydrogen bond, so it stops there. So let's do the next one. Chlorine's got 7. There's only 1 of them. Oxygen's got 6. There's 4 of them, so that's 24. Add that up, you get 31. Don't forget this -1, so add another one. 32. So it gives me 16 pairs. So chlorine goes in the middle. 4 oxygens, use up 4. I got 12 left. Take care of your oxygens. So I've used up all 16. So remember, oxygens will normally double bond unless there's extra electron in the way. So this is going to tell me right here how many you're going to leave as a single bond. I'm going to pick the top one. I'm going to leave it as a single bond. That means I've got to switch all of these oxygens, these bottom three, to a double bond. Okay, put my brackets around it with my charge, and that one's done. Okay, still 4 attachments. Still, it means tetrahedral. Tetrahedral. Okay, this was going to be polar because not all those oxygens are the same. This is going to be LDF, dipole, dipole. And there's no hydrogen, so I got to stop there. Okay, we'll do one more and then we'll move on to the next. So, arsenic has 5. Oxygen has 6, but there's 3 of them, so that's 18. I'm going to go ahead and add the 3. Okay, which comes out to be 26 electrons, which gives me 13 pairs. Arsenic's going to be in the middle. Okay, so I used up 3, so I got 10 left. Take care of my oxygens. I used up 9, I got 1 left, so that means there's leftover pairs going to go back on arsenic. So, this tells me how many oxygens I will leave as a single bond. Well, I only have 3, so that means I am done. So I don't have to move anything around. There is no double bonds. So this would be a -3. Now, don't forget this. This still counts as 4 attachments, so it's still going to be tetrahedral. But now my molecular geometry is going to be trigonal pyramidal. Okay, so this is not all balanced out, so it's going to be polar. So it's going to be LDF, dipole, dipole, and there is no hydrogen, so that means I cannot do anything with that. Now, I do want to jump up to one of these because, remember, these 2 are the exceptions right here. These 2 do not need 4 bonds because I want to talk about this because I feel like once some people learn double bonds, triple bonds, some people just start moving things because they feel like they have to. Okay, so remember I said starting at carbon, if it's in the middle, if it doesn't have 4 pairs, at least 4 pairs, you need to move something. So if I were to do boron or BF3, I'm going to go ahead and save us some time and go ahead and fill it out for you. So I'm going to fill up all these fluorines. And that was it. There was no leftover pairs at all. Okay, so some people, what they do is they think, well, boron has to have 4 pairs, so they start trying to do a double bond thing. And remember, it has to start at carbon. Boron is completely fine with 3 pairs. That means this one's done. So that means just make sure you're not shifting things around just because you feel like you need to. So it's starting at carbon. Do you need 4 pairs like this one? Okay, I'll go ahead and show you what this one is supposed to look like. Okay, so be careful with this. Do not start moving stuff over to help this beryllium out. Okay, if that was carbon, yes, go for it. Okay, but this is not. This is beryllium. It comes before carbon. So that means you leave this alone. That means it's done. Okay, so just watch out for that. All right, so hopefully that kind of helped with Lewis structures. So we'll kind of talk about these last few things, and then we'll be done. So we have percent composition. So basically all we're doing is we're just calculate percentages. So anytime you want to find a percentage, you take your individual divided by the total times 100. Okay, that's just what a percent is. If I ate 2 out of 4 pieces of pizza, 2 divided by 4 would give me 0.5 times 100 gives me 50%. So I ate 50% of the slices. So what you need to do is you need to figure out what are your individual masses and what's your total. Okay, so if I did calcium, okay, calcium normally has a mass of 40.078, but there's 3 of them. That comes out to be 120.234 because you will need all these individuals. Now, phosphorus, please be careful. This parentheses right here means this 2 outside needs to cross multiply into everything. So that actually means I have 2 phosphoruses. So phosphorus is normally 30.974. There's 2 of them. Comes out to 61.948. Okay, now oxygen, I actually have 8 of them. So 2 times 4 gives me 8, so 15.999 times 8 gives me 127.992. Now, I know all my individuals now, so that's the first part. Now add that up, and you get a total of 174 grams per mole. Okay, now I know my individuals, I know my total. So what I'm going to do is I'm going to divide each of my individuals by my total and multiply by 100. So I'm going to take this, divided by 310.174 times 100. Okay, and that comes out to be 38.76%. Do the same thing here. Divide by my total times 100. That comes out to be 19.97%. Do the same thing here, last one, divide by 310.174 times 100. And that gives me 41.26%. Okay, so that means that is it. That's your answers right there. So if you wanted to make sure you're correct, is technically if you added up those percentages, you should get pretty dang close to 100. Now, you may not get perfect 100, okay, because you rounded, but it should be pretty close. So that's how you do percent composition. So I'll kind of just do that one, and then we'll move on to the next. All right, so empirical formulas. Calculate the empirical formula of a compound containing 54.54% carbon, 9.90% hydrogen, and 36.36% oxygen. So first thing I'm going to do is for carbon, I'm going to take that percentage and I'm going to divide it by the mass you see on the periodic table. So I'm going to take carbon, divide it by 12.011. Okay, that's your first step, is just take your percentages and divide it by the mass on the periodic table. So that gives me 4.541. Okay, hydrogen, I'm going to take that 9.09, I'm going to divide it by 1.008. Okay, and that gives me 9.018. Oxygen, take that 36.36%, divide it by 15.999. That gives me 2.273. Now, what you're going to do is you're going to find the smallest value, which is this 2.273, and I'm going to divide everything by the smallest value. So divide everything by 2.273. Okay, so that gives me 2, 4, and 1. Now, these are all nice, clean numbers, so that basically means I'm done with this one. Okay, so that just told me I have 2 carbons, 4 hydrogens, and 1 oxygen. So there's your answer. I'll go ahead and do the next one, which is what it happens if you run into a decimal, so I'll show you. So carbon, I'm going to take that 49.5%, divide it by 12.011. I get 4.121. Hydrogen, I get 5.7% divided by 1.008, and I get 5.655. Okay, nitrogen, okay, I'm going to take that 28.8% divided by 14.007, and I get 2.056. And then last one, oxygen, I get 16.5% divided by 15.999, and that gives me 1.031. So I'm going to divide everything by 1.031. Okay, up top, I'm going to get 4. Then I get 5.5, so that's too far to round. So when I'm talking about, when you get these numbers, it may not be 4 exactly, but if it's like 3.98, 3.99, that's 4. Okay, but if it's something like 5.5, 5.25, 5.75, that's too far to round either way. So I'm just going to say it's 5.5. This one I get 2. This one I get 1. Now, what you do is basically you're going to start at 2 or whatever number you, sometimes you can just know right off the bat is, what could I multiply 5.5 by in order to get to a whole number? Well, that'd just be 2. Multiply it by 2, and that gives me 11. Now, in math, you can't just pick and choose. You got to multiply everything by 2 now. So that gives me 8, 4, and 2. So there's my answer. So I get C8, H11, N4, O2. Okay, so if 2 doesn't work, if you need to multiply by 2 and it didn't work, move on to 3. If 3 didn't work, move on to 4. Okay. Now, molecular formula, all you got to do is, the equation for that is basically you take your molecular formula mass divided by your empirical formula mass, okay, and that'll give you N, or the value to multiply your empirical formula by. Because remember, empirical formulas are just a simplified version of the molecular formula. Okay, it's basically a reduced formula. So in these questions, I give you the empirical formula and I give you the molecular formula mass. I don't know the molecular formula, that's what you have to find, but I give you the mass of it. So I'm going to take that 189.096, which is my molecular formula mass. I'm going to divide it by my empirical formula mass. Now, how do I get that? Is I'm just going to figure out what is the mass of CH3O3. So just add up 1 carbon, 3 hydrogens, and 3 oxygens, okay, and you get 63.032. Okay, so I'm going to take that molecular formula mass, divide it by that, and I get the nice number 3. That 3 is going to tell me what to multiply my empirical formula by. So I'm going to take CH3O3 and multiply it by 3. So my new formula is C3H9O9. And that's your answer. Okay, I'll do it again for this last one, then we're done. Okay, so I have my empirical formula. I have my molecular mass. So I'm going to take my molecular mass, so 118.088. I'm going to divide it by the mass of 2 carbons, 3 hydrogens, and 2 oxygens, which comes out to be 59.044. Okay, so take that, divide those, and you get 2. So I'm going to take C2H3O2 and multiply it by 2. And I get C4H6O4. There you go. And that's it. That's the answer. So please let us know. Hopefully that kind of helped out. Let us know if you need any help.